Now we'll look at entropy. And we'll do the same sort of a set of arguments which we did yesterday in looking at energy, internal energy for that matter. We have any two properties against which we are plotting here. And like yesterday, we say that we have two state points, 1 and 2, and the process takes the system from state 1 to state 2 along path A. During this time, there is some work transfer and heat transfer in the system. And then we complete the cycle by saying that there is one path which is B, which brings it back. And we also define yet another path by which we complete the cycle. This is C. And yesterday we looked at two cycles now. We have A plus B is one cycle and A plus C. This is the other cycle. Yesterday we looked at cyclic integral of heat equal to cyclic integral of work for this. Today we will look at cyclic integral of delta Q by T. So first we evaluate this, and we know that from Clausius inequality this is less than or equal to 0, and to begin with we will assume that equal to sign is applicable for reversible cycles. So we will consider that A plus B is a reversible process and A plus C is also a reversible cycle. So there are two cycles, both are reversible. So cyclic integral of this for A plus B becomes integral 1 to 2 along path A, integral delta Q by T, plus integral 2 to 1 along path B, delta Q by T, and this we say is 0. That's a reversible cycle. We are assuming that all processes are reversible. We make the same sort of a statement for A plus C cycle now. So this becomes integral 1 to 2 delta Q by T along path A plus integral 2 to 1 along path C delta Q by T. This is 0. And we subtract these two, and what we get is integral 2 to 1 along path B delta Q by T is equal to integral 2 to 1 along path C delta Q by T. And what this tells us is that integral delta Q by T from 2 to 1 is path independent. Whether it was B, C, D or anything else didn't matter. The only restriction we had put so far was that these were reversible processes. So we define, so this has to be a property. So we define the new property now, entropy ds as delta Q by T, which from this argument is come out from a reversible process, and also tells us that delta Q for a reversible process is TdS. Okay, so if we integrate this equation now, so we have integral ds 1 to 2 is equal to integral, I am just flipping on the states, delta Q by T, the left side becomes S2 minus S1 is equal to integral 1 to delta Q by T for a reversible process. So that is a important relation we've got that tells us what is the entropy change during a process. But what if the process were irreversible? Okay, so now we'll redo what we have done there. Going back, now we say that C, earlier we took this as reversible, now we take this as irreversible. And irreversible means that at every intermediate state is not defined, so this line should then technically be shown as a dotted line. So that's process C, which is now irreversible. And we develop the same things here, and what we get is A plus B remains unchanged, but A plus C is now an irreversible cycle. And so Clausius inequality tells us is that A plus C, instead of being equal to 0, is now less than 0. Here use. So what happens now? From the first equation, this is equal to 0 because that's a reversible cycle. So we get integral 1 to 2a delta q by t is equal to minus integral 2 to 1 by path b delta q by t. And this is a reversible process, so if we can say that if C were a reversible process, 2 to 1 C reversible, then I can put it this way. Okay, so what I've done is we've taken this first equation, taken this term to the right side, and that gave us this equation. And now we argue that instead of B, if this were C and C were reversible, then it will be equal, because this is path independent. We just showed that. Okay, so that's what we have done, and now we'll go back and put it in our this first equation, A plus C. So now we go back and see what happens to A plus C. So here you have integral 1 to 2, A is now replaced by this one, 2 to 1, C reversible process, so a minus sign there, plus integral 2 to 1 C, which is now we are looking at the irreversible one, is less than 0. So what it tells us, if we change things and flip a little bit of things, that this integral 1 to 2 delta q by t C reversible is greater than 1 to 2 delta q by t C irreversible. And the left side, we just derived that for a reversible process, integral of delta q by t over two states, which is here, is S2 minus S1. This will be greater than integral delta q by t when the process is irreversible. And that's one important inequality that has come about. And to make it equal, what we can do is say that S2 minus S1, I want to make it equal, so this term stays where it is, 1 to 2 delta q by t plus a minus sigma, which is entropy generation. Why plus minus sigma will come out a little later when we do some more analysis. But its implication is the same thing, that when Clausius inequality says it has to be less than 0, sigma should be a positive number. So this sigma itself is a positive number. Then things fall in place. Sorry, this is sigma, the entropy generation. In a cycle it will be minus, sorry. Okay, now let's go back and look at these equations. Say if it is a reversible process, and in a reversible process we say it is adiabatic, which means that delta Q is equal to 0, then S2 equal to S1. And this becomes nice for us because that's what we were talking of. And when we had the question that how can I make a Carnot cycle? And what we are seeing here is that there are two isothermal heat transfer processes. There is a reversible adiabatic process, a reversible adiabatic process, and we just saw that if it is reversible and if it's adiabatic, then S2 is equal to S1. That means during the process there is no entropy change. So this is an isentropic process. We looked at the second law statement, the Clausius inequality, which told us that cyclic integral of delta Q by T is less than or equal to 0. We looked at two statements of the second law, the Kelvin-Planck statement and the Clausius statement, both of which told us that certain cycles are not possible. We then looked at what would it take to make such an objective possible, and came about with the fact that it must have heat exchange with two reservoirs and have work input or output. Work output would be a heat engine, work input would be a refrigerator. And then we went on to look at what is the most ideal cycle that we can have. And that's where we came up with the idea of a Carnot cycle, where we said that every process is internally reversible and externally reversible. We saw that it consists of 4 processes, 2 isothermal heat transfer processes and 2 adiabatic work transfer processes, all of which are reversible. And that gives us the idea that we can construct such a cycle that is going to be the best cycle for a given TH and TL. And for that we calculated the efficiency, that the maximum efficiency, which is the Carnot cycle efficiency, will be 1 minus TL upon TH. TL is the temperature of the low temperature reservoir, which is the sink. TH is the temperature of the source from where we draw energy. So this gives us the upper limit on how good a cycle we can make, irrespective of what type of a cycle it is, what source we have, anything. And we put some numbers last time on it, that if I have a coal-fired power plant, what do I get? If it's a solar thermal, ocean thermal, we looked at many things and said, these are the type of efficiencies we get. They're all less than 1, and the real world, the actual efficiencies we get are even much lower than that. But that is the motivating factor why we need to do further development and research and come up with new technologies, is to try to increase that efficiency of the real cycle, knowing that the most ideal case will be the Carnot cycle, which I will never achieve, but the closer I get to that, the better it is. And the impetus for doing it these days is that when you make the cycle more efficient, for the same output, your energy input goes down, which means that your carbon footprint has gone down and you become a little more eco-friendly. So whether it is an aircraft engine or a coal-fired power plant, everyone is looking to go in that direction. So this was very simple, but a statement or a fact of very far-reaching consequences, which makes everything move in some direction. We then went on to look at, we defined entropy, and we said that how and what is entropy. For control mass, we got a relation ds is greater than or equal to dq by del q by t. And to make it an equal to sign, we said that we have generated entropy, which means that there was some irreversibility in the system. Because of that irreversibility, this entropy got generated. And our objective would be that in a process or in a cycle, can we minimize the generation of entropy? And basically, we are saying the same thing, that can we increase the efficiency of the cycle. So we got this equation for a control mass. The rate of change of entropy of the control mass ddt SCM is equal to entropy associated with all the heat transfers, which is the summation for every heat transfer that is happening to the control mass, which is q dot j by tj. J is individual heat transfer terms plus the rate of generation of entropy. So this is just the term for a process. This is a rate term, d by dt, but this is for a control mass. So that's one equation we have, and we left it at that point. Okay, I will take one more a little time to put up this equation, which is entropy generation or entropy equation for a control volume. The derivation will go very much the same way that we did for the mass conservation or energy conservation, whereas instead of energy, we are now looking at entropy. And the difference is that across the system boundary, we now are looking at where the heat transfer is taking place. So if say, that was the system, then our control volume, like before, encloses all the mass that is inside the control volume. And the way entropy, first we'll say, well, what are the inflows and outflows? This is just like what we had before. This is 1, and this could be called inlet I. This was exit E. And there was a mass flow rate associated with this, m dot I, and like that for every one of the inflows. And for here, there was the outflow, m dot E. And we say that a little element which we had considered last time, it carried mass, then it carried energy. Now it is carrying its specific entropy, Si. And this element that got out after some time, this carried its entropy, Se. And this is the control volume. So this will have SCV, which is the entropy of this, which we can write as M of the control volume multiplied by S of the control volume, the specific entropy. But entropy is associated with irreversibilities that will come, and also with every time there is a heat transfer to the system, there will be an entropy transfer into the system. So if at this point there was a heat transfer, then the system temperature there was Tj, and the heat transfer input here was Q, delta Q Cvj, then this caused an entropy inflow of delta Q Cvj upon Tj. So that's what it's doing, that every place where there is a heat transfer into the system, there is an entropy transfer associated with that. And then we can go about the same way that we did last time. And in the end, the equation that comes out will be that the rate of change of entropy of the control volume, rate of change of entropy of the CV, this has got the rate of outflow minus rate of inflow. It's on the other side of the equation, so it is looking like that. But what it is telling us is that this is rate of inflow with mass, rate of inflow with mass flow, mass inflow. This is rate of change with mass outflow, and this term This is rate of change of entropy transfer to the control volume across the system boundary due to heat associated with Q dot Cv. And in the end, we have this term S dot gen. This is the rate of generation of entropy. So that's the equation that we have been looking for, and it differs from the other two equations very slightly. So if I have to make a very general statement about all these conservation equations, we've said that something outflow rate minus something inflow rate plus something rate of accumulation in control volume is equal to rate of production or rate of generation or rate of creation. We can use any of those terms. And when we looked at this entity to be mass, we said that mass outflow rates minus mass inflow rates plus rate of accumulation of mass in the control volume. This we said rate of creation of mass, which is 0. There was also a question on the forum that also I will take up. Why are we saying 0 when there is energy associated with mass? So we'll come to that in a minute. We are saying that rate of creation of mass is 0. That is why we got this 0 over here. Then we looked at energy, and outflows were similar energy outflow, this energy outflow. Then inflow was Q as heat, outflow was work from the system, plus rate of storage of energy in the control volume, and this equates to the fact that rate of generation of energy, which it was 0, and that's how we got this equation. So outflow rate minus inflow rate plus rate of accumulation of energy is equal to 0. For entropy, things are a bit different. The outflow rates, inflow rates are the same. There is no work, no entropy associated with work transfer, plus accumulation of entropy in the control volume. This is rate of generation or the rate of creation of entropy, which is always greater than 0. Rate of generation of entropy will always be greater than or equal to 0, equal to, if it is a reversible process, greater than otherwise. And that difference which is there, we said that this is the rate at which entropy is generated. So there's a difference between these two conservation equations, where we say rate of creation of mass is 0, rate of creation of energy is 0, entropy, there is always a positive rate of creation of entropy. Okay, so that is what that equation was telling us. And now we have all the equations. We have completed everything that we wanted to analyze a control mass or a control volume going either in a process or a cycle. And we now have equations for all three: mass, energy, and entropy. So this completes the set of governing equations of the laws of thermodynamics, which each and every application must follow. There is no chance, there is no probability that any of these could be violated. The system would be impossible. Or there would be, if you are solving a problem, maybe we made a mistake. So this is what has come out of all this discussion. And we have reached the point where we are now saying that I can analyze any system I want, any machine I want, any device I want. We have now the tools, and we know that starting from here, if we make suitable assumptions, life will become a bit easier, but we have to make sure that all these are obeyed by that system. Okay, so this is one thing. We will then now look at some special cases and see how things work out and come up with some more concepts. Before that, let me go back to what I just said, that rate of creation of mass or rate of destruction of energy or creation of energy we have taken to be 0. And there is a question that suppose we have a container in which we put some oxygen and we put some fuel, say a liquid fuel or a solid fuel, and we ignite it. So initially it is all at the ambient temperature, Tm. We ignite it, this hydrocarbon completely burns into this, everything inside the chamber becomes very hot, and then we transfer this energy out, this heat transfer across this boundary, so that it comes back to T ambient. And one can argue is, well, you know, I got energy out of the same molecules which were there. Conservation of mass means every atom is still there. It may be in a different form of a molecule. For example, when we wrote CH4 plus O2 goes to CO2 plus H2O, we can balance this, 2 here and 2 there. What it tells us is that before the reaction we had 1 carbon atom, 4 oxygen atoms, 4 hydrogen atoms. And after the reaction, 1 carbon atom, 4 oxygen atoms, 4 hydrogen atoms. This is essence of conservation of mass. That at the atomic level we are saying that these atoms are still there, their mass has not changed, and so at the macro level the mass is still the same, the mass is conserved. So this we got carbon dioxide and H2O, but whatever Kg was there on this side is remaining as Kg of CO2 and H2O still there, and so mass is conserved. The question that if we took that much energy out, should not this mass be less? Because we have learned that E is equal to mc square. And that's a very valid question. So let's do a quick calculation and say, look, how much will be the change of mass? And we'll do a calculation where in this case, we take 1 kg of a hydrocarbon fuel, like say methane, we completely burn it and get the energy out. And we know from experience that for methane or for most such hydrocarbon fuels, the energy that you get out, which means that you burned them and brought them back to the ambient temperature, the question is how much energy came out. That energy is of the order of 40 to 45 megajoules per kilogram. So whether it's methane, butane, pentane, hexane, by and large, it is in the same ballpark, a little bit this way, that way. Wood, coals are less, wood is even less, but that's okay. We'll look at this particular case. So say we burnt 1 kg of a hydrocarbon fuel and say we got out 40 megajoules. So E is 40 into 10 to the power 6 joules. The question is, what was the change in the mass that took place? So if we do this calculation, the decrease in mass that we expect, this will be 40 into 10 to the power 6 joules divided by c square, which is speed of light, 3 into 10 to the power 8 meters per second, and this whole thing is squared. And if we take this calculation a little further, this becomes 40 upon 9. So we say this is about 3.5 into 10 to the power, this is 16, this is 6, minus 10 grams. So that's a very, very small amount compared to what we used of 1 kilogram. And so we are justified in classical thermodynamics as saying that whenever we talk of heat transfer, the associated mass change is negligible, and so we neglect this. It's way less, so nowhere near what we are looking at. And so the implication is that conservation of mass is independent of conservation of energy. This won't be the case when we look at nuclear reactions, where the change of mass in a reaction is substantial. Then we cannot do this. In this case, there will be a mass term, or here there will be a mass change term because of energy change, and here there will be a energy loss term which that reaction produced. So in classical thermodynamics, this is okay for us. These are two independent equations. They are not connected to one another, and we are justified in saying that mass change associated with energy change in classical thermodynamics is negligible. Okay, so that takes care of this aspect.